started. Okay. Yeah. Okay, so for today's physics club, we're extremely happy to have Professor David E. Kaplan from Johns Hopkins University. So within the high energy physics community, he's best known for a number of very creative solutions to beyond the standard model problems. He's also well known outside of the physics community for his movie Particle Fever, which documented the kind of time around the Higgs discovery. And so today we're very happy to have him to tell us about some modifications to the fundamentals or foundations of quantum mechanics. So go for it.
Thanks, Ian. It's great to be back. Some familiar faces. You guys seem to be doing extremely well. So it's fun to see you guys. I'm going to talk about something that I'm always a little nervous about it because it engages an emotional response from people sometimes a very strong response. And the way a dramatic blog posting might also engage or generate dramatic responses. So I ask you to join me and ask questions and stop me, and I will pause in places. The talk is packed full, so I may go a little fast in some places, so feel free to stop me. Yeah, that's just one. Okay.
Your cursor might be somewhere else.
There we go. All right. This is the century of quantum mechanics. I mean, last century discovered, but this century we are controlling it at just bizarrely elegant, beautiful, spectacular, and crazy levels. We can do things with macroscopic objects or macroscopic systems that are very quantum. We can put atoms wherever we want, place them in superpositions of states, entangle them with each other, measure incredibly, insanely small magnetic fields, make wave packets which are macroscopically spread out and yet still controlled. And as a particle physicist, somebody who thinks about how to test the fundamental laws, all of this is very exciting in the sense that now we're at a threshold where quantum sensing, or the kinds of sensors that one can build with very coherent, delicately generated detectors, can now test things like gravitational waves or large classes of dark matter in the universe, or even new fundamental forces of nature. And that excitement means we have to think about all of the types of things that one can test. It's not. But isn't that Zoom right there?
I was just told it's not.
And I'm a theorist, so you think I can solve this problem? Sure, yeah. No, I will. It says I'm sharing it. I can do new share.
Okay, then I think we'll just. Okay, I think let's just continue.
That is the Zoom, isn't it? I mean, I don't know. I'm waiting for someone to explain it to me.
Okay, now it's. There you go.
Okay, thank you. Great, terrific. Okay. If you can use quantum systems, atomic interferometry, or reimaginings of the Mossbauer experiment, which deserves its own talk, or just squid technology to test things like gravitation waves, dark matter, and new forces, we are diving deep into quantum mechanics to allow us to generate this in extreme sensitivity. And the obvious question is, shouldn't we be testing quantum mechanics itself? Now, this project came out of interacting with great people in AMO and other fields that are developing quantum sensors. And then they give talks about all the great things they can do. And then they talk about testing quantum mechanics. And I look at the theories they're testing, and I get very worried that maybe these theories either potentially don't make any sense, or maybe are already ruled out in much broader contexts. And is there a sensible, perturbative way to describe deviations from quantum mechanics? And so this is where this work started. Simple, gentle, perturbative deviations from quantum mechanics. Everybody in this picture is dead. And I'm sorry if you didn't know. There is nobody to bow to. It is time to think about, remind ourselves of the fact that though large, heavy, dense, sometimes overly complicated textbooks are written about quantum mechanics, those rules were made up by a bunch of people and then experimental tests, and we just have to ask, how do we parameterize deviations from that? How do we search for new physics? We have to think about at least generally how to parameterize it. So this is what this is about. How do we parameterize deviations from quantum mechanics? And what kind of deviation might we want? What should we modify? Probability. Einstein was the first to realize that quantum mechanics is probabilistic, and it made him nauseous. And people either still get nauseous about the fact that you can only have probabilistic answers to quantum mechanical questions, and yet hidden variables, Bell's inequality, for example, suggests that you can't describe things locally with definitive answers, like there's a definitive position to the electron in an atom. If the ground state of the atom had additional piece of information, which is the definitive location of the atom, of the electron in the atom, there would be an infinite degeneracy of ground states for the hydrogen atom. You turn on a tiny electric field, there should be a continuum of states at the bottom. We know that probability is an inherent part of quantum mechanics, and any local change, modification to quantum mechanics will not solve this problem. The hidden variable example is just one way to parameterize that problem. So let us just live with probability and ask if there's some other aspect of quantum mechanics that can be modified. The other property of quantum mechanics, which is remarkable, is that it's linear. Linear in the state. It means that you've found a solution to Schrödinger's equation, you find another one, you can use superposition, that's also a solution. It's remarkable. It's maybe not necessarily inherent, but it's this amazing thing that it's the only sort of fundamental law that we have that in some sense is perfectly, exactly linear. In fact, in 1960, de Broglie wrote this whole treatise on the fact that quantum mechanics is probably a linear approximation to some deeper theory, and then spent hundreds of pages trying to solve nonlinear Schrödinger equations. But there was just a sense that back then, it was okay to imagine such things. Steve Weinberg in 1989 wrote a infamous paper about nonlinear quantum mechanics. He added a nonlinear term to the Schrödinger equation, which you can think about as, here's a Schrödinger equation, think about it as adding to the Hamiltonian something that depends on the state itself. Steve Weinberg is a very famous physicist. He also passed away, I apologize, you didn't know. But because he's a famous physicist, of course, there were 27 experimental papers responding and say, oh, I'm going to test Weinberg's theory to 27 decimal places, and people did. The problem is that Joel Polchinski was a postdoc over there at the University of Texas, 3 months later pointed out to him that it was acausal, that it violated causality. It sended signals faster than light with EPR pairs. And so you can't just do that. And then back then, Weinberg gave it up. I think in the last few years of his life, he returned to it a totally different version. But it's delicate. And so if you want to add something nonlinear, something in the Hamiltonian, something that describes how a system evolves in time that depends on the state itself, you have to check many things. You have, of course, check all the things we know about the hydrogen atom and all the delicate sort of measurements and precise measurements that have been made in quantum mechanics, are they putting severe constraints on such a correction? And also we have to check that causality is not violated, and even just to understand what we mean by measurement. Okay. Something that will speak to this, the idea of, can this be a causal, meaning things don't go faster than light? That's what I mean by causal. Correction to addition to quantum mechanics is saved or could easily be explained if we embed this in a relativistic quantum theory, and that would be quantum field theory. So let me just talk about the framework for adding some small correction. Anything we add to the Hamiltonian, we would like to be local. We want to pay attention to the fact that things happen in space-time, and then something else happens, and if one causes the other, we want that signal to be light speed or slower. And so interactions, or whatever we change the Hamiltonian with, it specially picks out the position basis. So we like to magically talk about the Hamiltonian, lots of bases, but the position basis is very important for modifications which are nonlinear. So anyway, Weinberg gave some general attempt, even in the position basis, to have something that depends on the state. It worked beautiful for a single particle. It broke down for two or more particles, and Polchinski showed this in a very short paper in 1990. So we're going to add something very simplistic, which is we're going to add a term that is an interaction between the wave function and itself, and then we're going to include something, this is a retarded Green's function, and it guarantees that the interaction of the wave function with itself travels at light speed. So this is the Green's function for, it would be a massless field in a field theory, and this is the formal way of writing it. And I apologize because I will fluctuate to setting the speed of light and h bar to 1. So here is a Schrödinger equation. Here's my additional term, and that additional term then is nonlinear, depends on the state. Such terms do arise naturally in systems with many particles. Bose-Einstein condensates, say, where you don't worry too much about, light travel times. There's an interaction between the state and itself, but that's an interaction of many particles with themselves. Here we'd like to ask, can you add a term when there's only one particle? Is there a self-interaction possible between a particle and its own wave function? If you treat this object as just a correction to the Hamiltonian, albeit time-dependent, then you can ask, does this satisfy some of the properties you want for a Hamiltonian? And you can check quickly that this term is Hermitian. And because this is Hermitian, their Hamiltonian is Hermitian. And despite the time dependence, this thing is conserving the norm. So the sense of probability still makes sense. You can just then go on to add things like, for example, let's say this is a hydrogen atom or a harmonic oscillator, and you have a normal potential in here, and then you add a self-interaction of the wave function. If this epsilon is small, you can perturbatively find that there are still stationary states for this system. Those stationary states in general are not orthogonal, but they're stationary. The first 15 slides of this talk after the initial jokes are somewhat technical. And then it kind of will go off the rails a little bit. But we're going to try to perturbatively, carefully, delicately change quantum mechanics. So I have this slide. It's one of the more technical slides, but it's just a statement that the problem that Weinberg ran into was that if you have two particles, positions x and y, you would write an entangled state. Let's say the position part is entangled, which are products of the wave functions of either summed over a series of products. So the position of x, particle 1, is entangled with the position of particle 2. So what should be the form? If you have two particles instead of one of the correction to the Schrödinger equation, well, we'll put a Green's function for each combination. Particle 1 talking to itself, particle 2 talking to 1, and 1 to 2, and 2 to 2.
That question.
Yeah.
Can I conserve probability current?
Yes. Yeah.
Local?
Sorry?
Local power? Local?
Is the probability local? It is local. We'll see it's local. And energy is conserved in this system. Good look. These two terms are causal. These are communications between spatially separated particles. And these two terms you might worry or you might not worry. This is a particle 1 talking to itself, but this whole term does act on the full wave function, both particles. And so you have to prove that this term, if I say do something to particle 1, has no effect on particle 2 or vice versa in this case. And you can prove that perturbatively, that the effect on the x part of this system is unitary and does not affect particle at position y. Now, the reason that was the correct form to add to the Schrödinger equation is because you can ask, could this come from a quantum field theory? Quantum field theory is a description, just like in quantum mechanics, it's a quantum mechanical system, but now the Hamiltonian is made of fields. And those fields themselves would be operators that act on states on the vacuum, say, and create 1, 2, or many particle states. Nevertheless, in at least the Schrödinger picture, you can just simply write a Schrödinger equation again. There's a unitary operator, which gives you time evolution. And now the Hamiltonian is a spatial integral over fields. And so the question is, how do you add nonlinearities here? Hamiltonian, of course, can be highly nonlinear in operators. And the answer is to add state-dependent terms. This, by the way, is something that Kibble proposed in the late 70s under a different context, which I'll bring up later. So nonlinear, what I mean by nonlinear is to add to terms in the Hamiltonian objects that depend on the state. So instead of, say, a Hamiltonian, which will be a product of operators summed, there could be additional terms which look like operators, for example, times expectation values of operators. So average values of operators with respect to whatever the physical state is of the system. And as long as O1 and O2 are Hermitian operators, then you find again that this entire thing is Hermitian and the norm is conserved. So what you would do is you would say, take your favorite field theory. Here's Yukawa field theory. This is a fermion current talking to some scalar field phi. And you could add, for example, some nonlinear term. The nonlinear term would be, instead of just phi, I would add some epsilon times the expectation value of phi. This expectation value of phi is the average value of phi for the entire quantum state of the system. And you can treat this, perturbatively at least, as a background field. We can do quantum field theory with a background field. It's not, nothing goes wrong. And so at, say, order epsilon equals 0, you can compute in whatever state you're in what the expectation value is of that field, and then perturbatively compute at the next order in epsilon. You can take any operator in the action. So for example, you can take the coupling between the photon and a photon current and replace the photon with an expectation value. And in principle, if we can make it all work in a clean way, you can replace the field operator of the metric with its expectation value. If you go back to the Yukawa theory, here is my Yukawa term, a scalar field coupling to some fermion, current density, and an expectation value. And now you can ask perturbatively, can I just calculate that expectation value? So at leading order, classically, how would you calculate that expectation value? That expectation value is due to some, if this was, say, a photon, a charge density. But these fermions source the field. And so at 0th order and epsilon, whatever the wave function of those fermions are, wave function squared times the retarded Green's function produces the expectation value for phi. So now the wave function squared is just a source for phi. And the beauty of that is in the non-relativistic one particle limit, this is exactly the term that we would write in the Schrödinger equation. Okay. I've added this term, and now I can ask questions about what sort of violence does it do to the sort of physics we know and believe. For example, classical physics comes out of quantum mechanics so beautifully that it took us an additional 275 years to find it. So that means there should be some language in which we go from a quantum equation of motion, say time derivative of an expectation value of operator is the expectation value of the commutator of the Hamiltonian in that operator. From that we know in, say, single particle quantum mechanics, if we put x or p in there, we get very simple expectation values of classical equations. We can even choose particular states. So if I have a pendulum, we don't talk about the pendulum in quantum mechanical terms if it's macroscopic. So what do we talk about it in terms of? Well, the pendulum is effectively in a coherent state, bouncing back and forth, such that its expectation value of x really obeys an equation of motion that is truly classical. That the expectation value of x with very little uncertainty is rocking back and forth in a nice clean way, and its uncertainty doesn't grow in a coherent state. And so you can basically replace expectation values of products of operators with products of expectation values. Another way of saying that is that the commutators are not that important. The quantum-ness of the system is not that important. If you add nonlinear terms, let's say we add these nonlinear terms, state-dependent terms, you can ask similar questions about operators and what happens to the equation of motion. So this is sort of a mess. I've regrouped things, but all you're supposed to take away from all of this is the simple fact that here's an expectation value of a product of operators, and here's a product of expectation values. The point is that for classical-like states, or very classical systems, this expectation value is almost exactly the same as the product of expectation values. And therefore, this, for classical-like states, does almost nothing in terms of the visual effects. How would we determine it? In fact, what the nonlinear terms do, it makes physics a little bit more classical. And so that should then make you worried that for a very quantum system, some sickness should occur, something dramatic should happen. We've measured some very precise things in atomic systems, and so how will it affect these atomic systems? Just as an example, we could ask about atomic levels. We've measured the Lamb shift very accurately. We've computed the Lamb shift very accurately. We'd like to understand, does this mess this up? What is the Lamb shift? It is the energy transition between a 2s and a 2p state. And the amazing thing about 2s and 2p is energetically, they're almost degenerate. This is a tiny energy transition between these two. But their wave functions look completely different. And so if there's a self-interaction of the wave function, you would assume that it would correct the Lamb shift, perhaps dramatically. So why doesn't it do that? Or does this put it an exceedingly strong constraint? Well, the way we actually measure the Lamb shift is that we have the atom, which is a very small object if we're only focusing on the relative electron-proton position. And then we have the actual physical location of the hydrogen atom, which, if I could make a nice trap for it, it would be spread out over some large distance. Typically, the lamp shift is not measured this way. Maybe it's measured in a gas. And this spreading actually dramatically dilutes the self-interaction of the electron with itself, because the wave function that the electron sees is the full wave function. When quantum mechanics is linear, I can separate variables like the relative position and the center of mass position. But this coupling is a coupling between that electron and the center of mass position of the electron wave function. And if this was generated by an electromagnetic coupling, then we both couple to the electron and the proton. And so in fact, this distribution of charge in, for example, a trap of both the electron and the proton is almost effectively neutral. This wave function of the electron plus the proton produces a very tiny electric field contribution to the atomic state. And that contribution then makes it very hard to extract any sort of significant bound in this case. That volume suppression, and in the case of a neutral atom, the cancellation between the proton and the electron contributions of the nonlinear term produce something that ultimately, at best, if we're being generous, can put a bound on this epsilon parameter of roughly 10 to the minus 2. Can't be that that's the strongest bound on nonlinear quantum mechanics. Actually, the constraints just from past experiments naively come from sort of sillier things, which is that we've trapped ions for a long time. And if you look at traps from back in the 90s, they're quite shallow. And if the ion has a self-interaction with its own wave function, then it contributes non-trivially to the trap, and we would not have been able to trap the ion. In fact, if epsilon was bigger than 10 to the minus 5, the self-interaction potential becomes more important than the trap potential. And so the actual bounds come from this sort of weaker effect and statement, which is just the self-interaction of ions and the outside trap. Now, if whatever data or detailed information about the wave functions in this trap, for smaller values of epsilon, you might hope then we can learn something and we put stronger bounds on this self-interaction. And so there's a natural experimental test to do. You can trap ions in trap states, and you can put them in superpositions of trap states. In other words, you could take an ion, put it in a 0 plus 1 state with, say, probability amplitude p and square root of 1 minus p squared for each of the two states, and then recombine them with some pulses. And if nonlinear quantum mechanics is in effect, there will be self-interactions or interactions of each of this wave function with the total wave function. And the total wave function depends on how I've separated the two arms, p and square root of 1 minus p squared. So something inherent in nonlinear quantum mechanics is an effect on the phase difference between these two paths that depends on the initial preparation of the state, the properties of the state, and that phase, of course, also propagates in time. The longer the interrogation time, the bigger the phase. So there's potential for looking for these phases as a function of this parameter, the weighting of the 0 and 1 state. Hartmut-Hafner's group at Berkeley did such a test. They have beautiful ion trap system. They can interrogate atoms or put ions in a Paul type trap and put it in a linear combination of 0 and 1. And we've calculated what the phase difference would be as a function of the different weightings or probability amplitudes of being 0 and 1. and repeat the experiment many times, and lots of different tricks that I do not understand completely, but I could regurgitate, and then you'll ask me a question. I'll say, go ask these guys. Joseph knows a lot. And they did a series of measurements. They were able to do this a very large number of times, each shot 15 microseconds, and they took data for over a week. And they were able to put a constraint on this epsilon parameter. They measured a value for epsilon, which was consistent with 0 and less than 10 to the minus 11. So just keeping track of how the self-interaction works, that it's very local, making the trap as small as possible, long interrogation times, and the sensitivity to that initial state waiting, and then clever tricks to cancel any other phases that get imposed, allow us to put a much stronger bound with a few weeks experimentation and maybe a month prep. So this is something that could easily be improved. This is not necessarily an experiment that will be totally useful to us because of the way ion clocks work. But you can imagine if you trap an ion and then you look at a clock state of that ion, and there's a self-interaction between that ion and the clock state. And then you've chosen an ion whose nucleus is unstable. So at some point it will decay. So the actual state of this ion is an ion that's trapped and an ion that has decayed and is no longer in the trap, which means the full quantum state of the system is a particle which is in a linear combination of producing an electric field and not. And so over time, over the, say, decay time, the average contribution to the internal electric field is decaying due to this self-interaction. Now, the problem is clock states are usually chosen to cancel backgrounds, meaning stray electric fields. And so this is not an ideal way to test this. It's something that you, in principle, could test over the noise, but this is a sort of experimental test for modified quantum mechanics. Okay. A little crazy. Those experiments were sort of in the standard wheelhouse of AMO. And now we have to see what the consequences are of adding nonlinear terms to quantum mechanics. You're forced to have discussions like this. You teach, I don't know, first day when I taught quantum mechanics this year. First day, we talk about the Stern-Gerlach experiment. And Stern-Gerlach is, say, a spin 1/2 particle or a silver atom prepared in a state. Let's say we prepared it in a state which is in the plus x direction, and it goes through a magnetic field pointed in the z direction, orthogonal to that. And I can write down a Hamiltonian for that. And the Hamiltonian is the magnetic moment of the particle dotted into the magnetic field. The magnetic field depends on z, and so it'll put a force for the spin up, upward, and spin down, downward, or vice versa. And here is my initial state preparation. And then normally we say in the class, then you look and it came out of the top port, so it was spin up and you mark that down. And then you repeat the experiment n times, and you find 50% of them come out of the top and 50% come out of the bottom. But then you teach about time evolution, and you say, here's how time evolution works. The Hamiltonian has its mu dot b term. There's a kinetic energy term for the particle. And so what actually happens if you hit the unitary operator and time translate this, you get this, meaning the up part of the state gets a momentum upward and the down part of the state gets a momentum downward. So the momentum of the particle gets entangled with the spin up or down. And then it hits the screen. So you can say, oh, I measure it when it hits the screen. Or you can say, no, no, this is quantum mechanics. You know how to evolve the system. This is some system here. Let's pretend I knew the quantum state of the screen, and I would time evolve the system. And there's a Hamiltonian term that tells me, oh, if the thing hits up here, it lights up a pixel. And then if the thing hits down here, it lights up that pixel. And so I time evolve this with that Hamiltonian, and I go from this to a linear combination of this upper pixel has been lit and this lower pixel has been lit. Both are parts of the wave function, and then everything else which is not affected by it. Then I walk into the room, and when I look at the screen, the light on the top goes into my eye and hits my optic nerve somewhere in the back of my eyeball, and it sends some signal to my brain. If it's up here, it sends it down here, and then if it's down here, it sends it up here. And so what happens then, I have time evolved due to this extra term in the Hamiltonian, which couples that light to my optic nerve and tells me how to evolve this state. And at this point, of course, we've thrown out this piece over here. There's no reason to keep this piece, because now I'm involved and I want to do further experiments. And if I time evolve this, I put my particle or the screen or whatever lives on this part through more experiments. I will continue to time evolve it. This me who saw the pixel up there and has made decisions based on that. And then there's the other part of the wave function, which also Hamiltonian describes this time evolution. And so people don't like this description. It falls out of just unitary time evolution in quantum mechanics. So then we say something like, oh, the wave function collapses. A measurement's made, something happens. Blah, blah, blah. I don't understand this system. I do a projective measurement, decoherence. We have all kinds of beautiful words to say, don't think about this over here. And you don't have to, because once this system has got so complicated, these two states will never re-interfere. They'll never come back to you. They're not important, so this is not important. So in linear quantum mechanics, you can always start fresh, dump something. I call it the disappearing worlds interpretation of quantum mechanics. You just get rid of that thing and just keep going about your business. Don't worry about it. Okay. But so the language for measurement in quantum mechanics is there's a system, there's a measuring device, time evolves such that the system and the measuring device interact, and you get a linear combination of the terms, the pieces that are diagonal in that interaction, and the outcomes of the two measuring device results. And you'd say that the state evolves into this linear combination of entangled, it's an entangled state of the spin and the measuring device. And we assume that the measuring device outcomes are orthogonal to each other. Maybe they're stationary states once the particle goes away. And so that orthogonality makes it trivial to average over, sum over, trace over the degrees of freedom of the measuring device. And what we really then say is the outcome is a mixed state with different probabilities of measuring, say here, spin up and spin down. That's the language we use. It's extremely useful in linear quantum mechanics. But if there are nonlinear terms in the Schrödinger equation, stationary states are not actually generally orthogonal to each other. That this tracing operation that one does to get rid of those degrees of freedom can produce some trace amounts of measurement noise associated with, say, particles that spin up, but we measure spin down somehow. So now it depends a very detailed way on that Hamiltonian. And let's see then how would one describe it. My experiment is a spin, prepared spin half in the x direction, and an experimentalist or a robot that does not have consciousness, or somebody is not sentient, or whatever the ethics of the university allow, and this laser and two photodetectors. And the initial state of the system is so in such a way that this spin is not in any way entangled with this system. And now my goal is to construct or create a macroscopic superposition, the way it looked like in the Stern-Gerlach experiment, which is to say that we now take that state, make a measurement, and we end up with a spin-up possibility outcome. And in that possibility outcome, the robot or electronic device, whatever it is, turns on the laser pointing to the photomultiplier on the left, a very low energy laser. And if spin down is measured, or when spin down is measured, the laser is turned on and pointing to the right. And so now we're in a state, which is a superposition of spin up. The left laser is turned on, and the environment associated with a laser pointing to the left describes the state, plus spin down, laser to the right, environment responding to the laser pointing to the right. So we might describe this as saying, well, the Hamiltonian has a contribution, which is that photons couple to charge densities, interacts with charged particles living in the photodetector, for example. And so we might ask about transition matrix elements that involve, for example, if I'm interested in living in the left world, now I can ask, what is the expectation value of the left part of the photon field and the detector that might see it, and that will be non-zero. And in the region to the right, for the part of the state that saw only spin up, that part should be 0 because there's no laser turned on over here. And this is because in the region of x right, this region, the laser is 0, or the electromagnetic field, coherent electromagnetic field there, has 0 amplitude. Now, nonlinear quantum mechanics, the suggestion then is, what if there was a term in the Hamiltonian which was not an operator, but an expectation value of the electromagnetic field? In this case, both the upper term, meaning this expectation value on the left of AJ and the expectation value of the right of AJ would be non-zero, because A mu itself in the full wave function, which is a combination of the top and the bottom, is non-zero on both sides. And so by putting an expectation value in there, you've done something very dramatic, actually. You're now sensitive to the full wave function, even if there is a macroscopic difference between the two parts of the wave function. The amazing thing, if you have nonlinear terms in quantum mechanics, decoherence is your friend. You can amplify quantum effects by doing a quantum measurement and having macroscopically different outcomes. Polchinski understood this when he showed Weinberg's version did not work, but that there are versions that should work. And he said communication between arms of the wave function, he called the Everett phone. Alex Sushoff's group at BU set an Everett phone-like experiment together at BU. And the idea was to generate bits, zeros or ones, and from that bit generator, make a decision through some control computer to turn on and off an electric potential, which then can be measured. And the idea would be when the potential was off, of course, we should measure something close to 0. And when the potential is on, you measure a regular 3-volt potential. And the idea here is that the bits that we're instructing this decision whether to turn on and off the potential was a mix between classical random bit generator, just a series of random numbers from a computer, using IBM to generate quantum decisions, spin up or spin down, 1s or 0, from quantum measurements that they say have high fidelity, and then something in Alex's lab, which were measurements of nuclear spin that are done with low fidelity, but still depend on quantum measurement probability. And so these bits were produced, scrambled randomly, generated into the control computer, made decisions about voltages on and off. And the question was that depending, when you unblind this analysis, do you get, when the voltage is turned off, a non-zero voltage measured from some other part of the wave function? And they did a measurement and didn't see anything up to 5 times 10 to the minus 11. So indeed, another test, but a crazier sounding test, which depends on the fact that macroscopic superpositions are, at least from just standard unitary evolution in quantum mechanics, possible. This leads to a next natural issue, which is nonlinearity is very delicate. So, say experimentalist at Hopkins, she was super excited I was giving this talk, and she said, I'm going to test your theory. I'm going to do better than Alex's, da, da, da. And she set this thing up, and she did this sort of laser, the experiment. She thinks she gets to 10 to the minus 13 to whatever it is, and got a result and discovered nonlinear quantum mechanics. It's going to revolutionize all technology and everything. Great. And then she wants to repeat the experiment. The only problem was that the part of the wave function where the laser pointed to the left, while it worked just fine, the part of the laser pointing to the right somehow blew up the photomultiplier and fell over, and there was a fire in the lab, and it was a disaster. And so this version of the experiment, this part of the wave function, could not repeat the experiment 2 days from now. And so the wave function after October 26th, 9 a.m., when she was going to do the experiment, looked like the laser wave function pointed to the left originally, repeating the experiment, producing this linear combination. And then on the right, nothing happened. So it remained in the state. So nothing interesting happened for the other part of the wave function. And so the state after October 24th looked something very simple, clean, and like this. But the state on October 26th was this much more complicated situation. And now if you compute that expectation value on October 26th of seeing a laser where you shouldn't, it's half the value of the experiment on October 24th. And now she thinks she's going crazy. She better not tell her colleagues about this because it doesn't look very repeatable. So in order to get the full effect, both parts of the wave function have to produce the experiment at the same time. I call this quantum pollution. So without adequate care, you have to make sure to all parts of the wave function repeat this experiment, which then suggests another issue, which is that maybe there's a lot of quantum things that have happened in the universe before this. Maybe there's been a lot of dilution, not just blowing up a photomultiplier. You could ask the question, what part of the wave function of the universe are we? Maybe we're a very small part of the wave function of the universe. What do I even mean by we? Well, me giving this talk, what is my center of mass distribution here? I don't know. I thought it was very small, but maybe there was some effect in the past that caused me to do totally different things. And I'm only a small part of the wave function with an amplitude alpha. And so then if I am allowed to turn on a laser in somebody's laboratory and I calculate expectation values of, say, a mu at that location, it is dwarfed if, for example, alpha is much smaller than beta. If only this small part of the wave function turns on the laser, an expectation value for the electric field in that location is suppressed by alpha squared. In linear quantum mechanics, that alpha squared is there too, but it's everywhere in the Schrödinger equation. We just get rid of it. We renormalize states. Can't do it if you have a nonlinear term. If you have something that's higher power of the state. So this suggests that if there was dilution in the past, that we would lose the ability to exploit nonlinear quantum mechanics. It's kind of suggestive that linear quantum mechanics may be an attractor solution in our universe. It could have started super nonlinear, but whatever we do now looks quite linear, and maybe that's why. You could ask, is there any possibility that the world could have evolved super classically, so that whatever the initial conditions were, wave functions were very small, Gaussian, small errors, small uncertainty, and all the physical parameters? Could it be the initial conditions was such a way, and then the entire evolution of the universe didn't really pollute the wave function? That I really am standing here in the entire wave function starting from the beginning. It sounds crazy, but you can look at physical systems like the sun. Let's say the emission of every single photon from the sun was a quantum probability. Goes to the left, goes to the right, up, whatever, and just randomly emits photons over time. And now you can ask, over 10 billion years, what is the center mass distribution of the wave function of the sun? From the kick from every photon released. You can calculate it. It's less than 100 nanometers. So the sun is not, even though every particle comes out, are we splitting the wave function? The sun is not really distributing important macroscopic parameters like where is the sun very much. You need something a little bit special. Of course, the sun is full of enormous number of particles, but even just the coherent motion of hundreds or thousands of particles is enough to exponentially suppress the possibility that the universe looks macroscopically different in different parts of the wave function. The natural thing to ask is, what about the weather? Is that controlled? That's a chaotic system and quantum. What about my brain? What if I thought I'd get lunch, but I decided not to? Was that a single spin in my brain, one ion? Well, even to get a single neuron to fire requires a lot of charged particles. It's quite classical, at least up to the point we know. We don't know. Maybe consciousness has something to do with quantum mechanics. I always think that consciousness is such a hard problem, and people say, well, quantum mechanics was such a hard problem and mysterious, probably it's the same solution. And I think, well, probably not. It's probably something else, which is also mysterious and harder. So I'm not convinced that these sort of things, which look like they're driven by many particle systems in some quasi-equilibrium way, care about quantum mechanics. So that perhaps it is reasonable for the universe to be classical. Except for our stupid field of particle physics, which is that a big machine will measure a resonance in 2 photon energies summed at, say, for example, 750 giga-electron volts, and then 500 papers will be written by my colleagues about that little bump there. And what if that 3 sigma deviation was quantum mechanical in nature? We live on some 3 sigma tail of the wave function of the universe. This thing has polluted my wave function dramatically. Not by 10 to the 100, but by 3 sigma. I've already lost power in my ability to convince people to perform experiments, potentially by a factor of 1,000, assuming that this went away because it was quantum statistics that produced it. Does that mean the last 100 years of our deep knowledge of quantum mechanics has totally screwed this up because we've been diluting it with all these experiments? Normally, when we look at outcomes of quantum experiments, we look at them statistically. We're not measuring a single spin. That's quite hard, but we see statistical outcomes. And so a lot of experiments do not have this issue, but outliers like this, if they're quantum mechanical in nature, might have an effect. What about life? RNA, people don't really know how RNA formed in the early universe. It's this very complicated molecule in a very hostile environment. Is it possible that life is a very, very tiny part of the wave function? It's a tiny part of the wave function where RNA survived long enough to start reproducing and then produce enough life. Or maybe it started, but at sort of macroscopically different times. Or maybe evolution itself, which depends maybe on a few particles, something messing up a single DNA strand that gets amplified. We are amplifiers of these tiny little bits of information, this DNA, which then gets copied robustly and produces amazing systems. So you could imagine that on Earth here, the wave function on Earth that describes the system is a linear combination of people, life, animals, all kinds of things, and no life. And maybe no life dominates this universe. Or maybe evolution somehow changed things, and we have all kinds of different types of life on the Earth because evolution just worked differently in different parts of the wave function, and SETI should point all of its dishes downward to look for weird signals of electromagnetic radiation that we do not create. This is the kind of conversation you're forced to have. Well, what if that's true? We've totally diluted things. That's terrible. Maybe maybe fundamentally quantum mechanics is nonlinear, but we cannot control it. But on the Earth, let's say we believe that the magnetic field is there in all parts of the wave function. if it's there in all parts of the wave function, and we can only control a tiny bit of it, what you could imagine is constructing a very successful magnetic shield, put a squid inside of that magnetic shielding, and look to see if we measure the expectation value of the magnetic field of the Earth in all other parts of the wave function. The shield is only there in our tiny part of the wave function, but the magnetic field is there everywhere. And so in principle, this would be a way of testing the case where nonlinear quantum mechanics got dramatically diluted. In fact, this, in this scenario, puts a bound on that epsilon of about 10 to the minus 5 because magnetic shields work. And we do very sensitive experiments behind magnetic shields. But let's go back in time. What about cosmology itself? The beginning of the universe. So people get very excited about a specific model of the initial stages of the universe. It's called cosmic inflation. One miraculous thing about cosmic inflation is that it is described by a quantum state which is extremely homogeneous and isotropic. And yet we look around the universe and we see something that's dramatically inhomogeneous and anisotropic, except at the largest scales. So how could it be that this almost perfectly homogeneous and isotropic quantum state produced us? The answer is that the current wave function in the universe perhaps is extremely homogeneous and isotropic. We just live in one tiny little bit of the branch, but on average, on all parts of the universe, and this is what inflation would predict, all the different parts of the universe together on average produce something which is homogeneous and isotropic. So most of the universe on average then is something homogeneous and isotropic, and in most of the universe, our Earth is located somewhere where there is nothing. There's no Earth here, no sun, no galaxy even, in the vast majority of the wave function. What to do then? Well, you would test quantum mechanics again, nonlinearity in quantum mechanics, because if, for example, things that couple to the gravitational field or the gravitational field itself have nonlinear terms, then the metric that matter couples to will be a combination of what we see in our universe, let's say a star, our sun, or the star at the center of the galaxy, and the orbits, plus an average metric which will locally look like flat space. And so if something of this type exists, we would expect that the metric would act as, for example, linear combination of Schwarzschild and flat space, locally flat space. And then if you combine those and expand and renormalize, you get second order GR effects in orbits, which we have not yet measured, but in principle would be measurable. So even in the case where the situation dilutes dramatically, then there are ways in principle to test it. All right, one last slide on the implications. Let's say we're lucky in the sense of the universe evolved very classically. RNA production really was a collective quasi-thermal or out of equilibrium, but many particle effect. And most of my wave function is right here in this room. What could I do? What could I do with local nonlinear quantum mechanics? It means I could parallelize any computation and get out the results. So all I need is a laptop and a few spins, and I decide with every possible measurement of a few spins, I'm going to do some fraction of a computation on my laptop. And so I measure the spins, whatever outcome I get, I run that part of the computation. And so now the wave function is a superposition of the laptop running 8 different processes in that case. And then once the results show, I have a screen and a decision beforehand that depending on what spins I measure, I will flash with laser light the solution, the output of this computation. And now I will be able to do it for all of them. And any of the observers, so all of this is true in regular quantum mechanics, but if quantum mechanics is nonlinear, any of the observers in any of these branches of the wave function can see all of the results, which means you can use quantum mechanics to parallelize classical computers. You could parallelize other things. You could decide, I want to look for water in the desert, and you only have one little scanning device. And so you measure a whole bunch of spins, and in each part of the wave function, you send the device to a different part of the desert, do some scans, do some digging, and at the end of it, you come back, look at your screen, and find out which of those devices found the water, and then you know to dig there. So we convinced ourselves to be totally panicky about this and ask if you could break 256-bit encryption using a Cray computer if this was really true, and you could parallelize it. And at the time, the bounds on epsilon were only 10 to the minus 5, so we were very worried about it. And we decided that you could only do 128-bit encryption in about a week. 256 required longer than the age of the universe, so we put the paper out. Quantum computing. All right. Conclusions. There's a consistent way to explore nonlinear deviations from quantum mechanics. And locality makes, it turns out, past tests quite insensitive because they didn't take into account the locality of the entire system to look for those self-interacting effects. Nonlinear effects can be experimentally tested by amplifying quantum measurements. This is creating macroscopic superpositions. And quantum amplification, though, on the history of the universe, suppresses the local potential for manipulating a system and creating these superpositions that are observable. And in fact, linear quantum mechanics in that sense locally is an attractor solution. If locally diluted, non-zero fields across the wave function could be detected. That would be the Earth's magnetic field if the Earth was here in the majority of the wave function or a significant part, or cosmologically, say the metric or any background field in the universe that should be there across the wave function. And finally, if nonlinear quantum mechanics is locally accessible, it will radically change what we can do technologically. And that's it. Thank you.
So thank you for the very provocative talk. So are there any questions? And maybe we can start actually with the one that just popped up in the Zoom. If you could,
yeah.
There was, I think, well, other people composed their question.
Could you put bounds on epsilon from Bell-type experiments? Yeah, that's a great question. What we discovered is that in order to put bounds, you want to maximize the self-interaction. So Bell-type experiment doesn't focus on the localization of the state. And so the overlap of the state is very important. And the spread of the total wave function in the state relative to, say, individual bits of it can dramatically suppress the effect. So I'm asked often by particle experimentalists, you know, we in a sense do quantum mechanics very precisely in a particle experiment. We're looking at probabilistic outcomes like we described, and we're probing very deeply at very short distances. But those beams are microns in width and centimeters long. Even quantum mechanically, the wave function of those particles are very spread out. And if you compute the nonlinear quantum mechanical effects, they're extremely diluted. And ultimately, if these nonlinear effects are very similar to the actual operators in the Hamiltonian, then you don't see much different beyond the standard responses. See.
Can you connect that answer to Polchinski showing that you could have superluminal communication with cells?
Yeah, so what Polchinski showed is that essentially if you don't put in that Green's function, you'll get superluminal propagation. So it's not intrinsic. The system is inherently Lorentz invariant and satisfies causality. But because you start with an initial state, it's like you put in a background. And that background does break translation invariance and boost invariance, but not in an a-causal way, turns out. Yeah.
Yeah,
Sorry.
thank you for dispensing with hidden variables.
Hey, Steve.
And you had the density matrix on one slide, and a lot of what you showed was written in terms of the wave function.
Right.
What if there is no wave function? What if that's just an illusion? It's a computational intermediary toward getting the density matrix. Can you recast all this in terms of the density matrix? And you know, I have a feeling you can, but I don't see it offhand. Or if you ever thought about that or looked into it.
We did, and you can put everything in terms of the density matrix. So we could have rewritten. I think in the paper with Alex Sushkov, reviewer asked for something like that, and maybe you were the reviewer, but we did talk about it in terms of the density matrix and tracing over states. The density matrix, of course, if we don't believe in the wave function, offers other ways to violate quantum mechanics with Lindbladians or other things that look like, that violate, don't violate probability, but violate unitarity in the spirit of quantum evolution. So, and I think that's very interesting too. So maybe the underlying theory is truly non-deterministic. Maybe outcomes really are probabilistic. Here we've preserved unitarity, we've preserved probability, and that you only see if you do it in terms of the wave function.
So I understand that you can make quantum mechanics non-local, but is there any good reason why it should be?
Nonlinear.
Nonlinear. But is there a good reason why it should be, in the sense that supersymmetry was a good reason to it, because you could address potential hierarchy problem?
Great.
Is there anything which would
pushed us in that direction?
Yeah, which would become easier, like combined quantum mechanics with general relativity. I mean, from what you said, it looks like there are many good reasons why it better be non-linear.
Yeah, as in terms of the fundamental description, so we're not trying to solve any problem. The supersymmetry was trying to solve some kind of problem. Didn't seem to solve that problem, but you know, that's not what motivates it. The question is just to parameterize deviations, and in principle, we can test those things. Now, once you say that the fundamental theory itself is nonlinear in some way, maybe it's the steps to a more complete theory. And the interesting thing about this correction is it's not an energy-dependent correction. It doesn't tell you, look at high energies, and that's where everything changes. That's where quantum gravity becomes important. It's something else. It's some very small parameter which environmentally has become naturally small. So that means if you have ambitions to formulate a fundamental theory, this is potentially a very different avenue to walk into, starting with something assuming state dependence in the action. It picks out particular things, it picks out locality, which is what field theory wants you to do. And maybe it tells you how to reformulate the path integral. And it does potentially tell you new things about quantizing gravity. It's our hope.
Yeah, I had a bit of a question about the computer science implications of this.
Yes.
So you can get this from like writing down like a QFT with this like expectation value term and taking the single particle limit. But that gives us nonlinear quantum mechanics, which we know can solve NP or sharp P complete problems. So this isn't true in our universe, but could we potentially like say something about the types of QFTs that are simulable based on like the fact that if we could like simulate this QFT through some sort of like Jordan-Lee-Preskill algorithm, we could use it to solve NP complete problems?
I have no idea. Steve, do you have any idea? No, I have no idea how to combine this with known algorithms in quantum computing. Haven't thought about it.
Thank you.
Sure.
Maybe one more question if anyone has an urgent.
Hey, Dave.
Hey, so you looked at a correction which was cubic in the wave function.
Yes.
Could you look at other powers?
Sure, and they naturally occur even. So you can decide that the field theory is fundamental and that the Schrödinger equation in the field theory is exact. So epsilon maybe is small, but that's the exact new term. And then you can compute the non-relativistic limit. The non-relativistic limit will have higher order terms in it, for sure. We have not computed those because we're putting bounds on the linear term as well. So in the non-relativistic limit, we are taking an approximation that's not necessary. When we talk about things like detecting coherent fields, like the electromagnetic field, there we are doing the full theory. And so there you could ask, can I add additional terms? Can I put multiple expectation values around things? And ultimately, we haven't found anything non-trivially different than what we see. Remember, putting expectation values around lots of operators is like making it more classical. You're removing commutators, essentially. So you're just adding more and more classical-like terms to the action. So I don't predict it will do anything non-trivial.
Okay, so let's thank David again for the great talk.